Hey everyone, Morgan here. We're back now on page 2 of the kinetics outline for AP Chem, and we're introducing the idea of a rate law. Now, a rate law isn't a law in the sense of a bunch of words that say something you have to do or not do. A rate law is an algebraic equation. The rate of a reaction, capital R, equals a constant, lowercase k, times the concentration of some species raised to different exponents. We'll call that y. Sorry about that. So x and y. Now x and y are going to be referred to as the order of the reaction. Capital R is the rate. And down here we have molarities. And K was called the rate constant, which is a proportionality constant. Which is necessary to set these equal to each other. Now, as a general statement, K is big for fast reactions, and K is small for slow reactions. So the numeric value of K will be big for a fast reaction. It'll be small for a slow reaction. I want to emphasize that this is a lowercase k. There'll be a capital K popping up in the next chapter. Okay? So, reaction orders will always be determined by doing experiments. We don't just stare at an equation and write a rate law. It doesn't work that way. Okay? There are two ways of expressing rate laws. The differential, which pretty much looks like this, R equals K times A to the X times B to the Y, and one called an integrated. If you are recognizing these terms from calculus, you are correct. That's where they come from. Don't worry, you don't actually have to do any calculus for this to work. Okay? But an integrated rate law will always take the form of y equals mx plus b. It's a straight line. Okay. Now, let's show you some examples of how rates change as concentrations change. So we're going to consider a rate. It's first order in 2 molar A and in 2 molar B. So when I write the rate law, R equals K times the concentration of A. Since it's first order in A, the exponent's a 1, and it's first order in B, the exponent for B is a 1. Okay? Now, let's make up a value for the rate constant. We'll just call it 1 to keep the math simple. This equals 1 times 2.0 to the first times 2.0 to the first, and that equals 4. Now, what would happen if we increased the concentration of A? Let's double it. This time, instead of 2.0, it's 4.0 raised to the first times 2.0, and this equals 8. So what this is saying is when you double the concentration, it equals double the rate for a first order reaction, not for other order. So now this time we have a second order reaction in terms of A. R equals K times A, and that would be squared. That's how it looks different for a second order. It's B. So this equals 1 times 2 squared times 2, which equals 8. And if I double the concentration, the rate now is 1 times 4 squared times 2, which equals 32. So when I have a second order reaction, if I double the concentration, I get 4 times the rate. The rate goes up a lot because it's second order. Now, what if I triple that concentration? Okay, R equals 1 times 6 squared times 2, which equals 72. So when I have 3 times the concentration, I get 9 times the rate. Okay? So that's coming from the concentration being 3x squared. And 3 squared equals 9 times faster. Okay? Now, third order, pretty straightforward. I think now R equals K times A to what exponent? Yeah, I heard you, the third, times B, which equals 1 times 2 cubed times 2, which equals 16. Yeah, 16. So now I'll double the concentration of A. 1 times 4 cubed times 2 equals 128. And this means it went up by a factor of 8. That's because 2 cubed equals 8. All right, that's it for page 2. Tune back in. We'll look at examples of this on 3 and 4.